Hello everyone, go ahead and take the time right now, get out a sheet of paper and practice writing out the formal definition of the limit of a function in symbols. Very good chance something like this will be asked of you on the test, the next test, which will be next week sometime. Alright, so if you're ready, let's take a look at, again, what this means in symbols. We always just want to start with the limit notation, so the limit of f of x as x approaches a is equal to L implies that for every or for all epsilon that are greater than 0, and again it just means that those are given to us, there exists a delta greater than 0 such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is less than delta. And then still we should put in greater than 0 just in between. But absolute value indicates that it is going to be positive. All right, so there is the formal definition of a limit of a function in symbols. All right, next I want to take questions, so please let me know for my remote learners at the Zoom meeting today if you have any questions over the quick review or gift tutu. You can even email me ahead of time so I know which ones to possibly look at and have ready for you by the Zoom meeting today. All right, I also want to show you how to graph a piecewise function on the Inspire calculator. So if you go ahead and get that out, because I know number 3 from the quick review had you graph a piecewise function, but just as a way to check on the calculator, especially if you can't graph by hand, then you are to just graph on the calculator to determine the limit. So let's go ahead and take a look. Okay, so if we're in the calculator, go to the calculator page, or add graphs, rather, not a calculator page, but add graphs. All right, and we want to choose the button right next to the 9 here. So we're looking at all these options, and if you notice the one I have it highlighted on, so we have like a bracket, and then we're going to be able to, we have a template here to type in our function, and then with our constraints as well. So go ahead and hit that. And I'm not going to type in number 3, I'm just going to make up a simpler one. So right in this first top box here, let's just type in x squared, and then just hit over, and let's say our condition here, our constraint is that x is going to be greater than or equal to 1, so just hit x. Then if you hit control equals, you could change to an inequality sign, so we want greater than or equal to 1, and we'll go to the bottom first box here, let's type in a negative x, and then the next one is just going to be x is less than 1, so again hit control equals, and then we'll go less than 1, and then just hit enter, and then there's our piecewise function here. All right, so just a nice way to practice this, just to show you all different types of graphs of functions that we can do on the calculator. Or maybe you already knew that. All right, but there's an image of what we just did. All right, go ahead now and get out your logs day 7. You can check your answers. I'll scroll through slowly. Again, pause the video at any time. Now, if you notice for A, it looks a little different because what we could do is take this and rewrite it exponentially, so it is backwards. We're getting x is equal to 1/2 to the y. So you can make a table of values and then just pick your y values here and then raise 1/2 to that power and then fill in the x values. So that's a simple way to go through and do that. Take a close look at part C. Again, for part E, I let that equal u, and I rewrote it exponentially. You didn't have to take the natural log of each side. Any log of any base would work. As always, let me know if you guys have any questions on this as well. All right, so we're still in section 2.3. I had you guys read over some pages, so I just want to emphasize on page 77, there were some statements here for continuous functions, and this is what I started to mention when we looked at the definition of continuity and then the types of discontinuous functions as well. So the graphs we were really looking at were for all x values, all real numbers for x values here. However, we can close it off to a certain interval. So a function is continuous on an interval if and only if it is continuous at every point on the interval. So again, we would have to go through the definition for a continuous function just to make sure that that's true, but it doesn't have to be from negative infinity to infinity on that domain. We're just looking at a certain interval or the actual domain of its whatever its domain is. So a continuous function is one that is continuous at every point of its domain. So even if we were looking at y equals 1 over x, yes, it's discontinuous at x equals 0, but 0 is not in its domain. So we could say y equals 1 over x is a continuous function over its domain, meaning excluding the 0. And a continuous function need not be continuous on every interval, just on certain ones. So we could even think of the graphs of y equals tangent x. If we just stayed on the interval between negative pi over 2 and pi over 2, again, not including those, but those would be the asymptotes, but everywhere in between, it could be continuous, but it need not be continuous on every interval that we create for it. So these are just some things to keep in mind. All right, and theorem 7 on page 78, it was a composite of continuous functions. So this is, again, just a little checklist that we can go through. Composition of continuous functions. So if g is continuous at x equals c, and then f is continuous at x is equal to g of c, then f of g of x is also continuous at x equals c. So we're just going to go through a little test here, an example. So I'm kind of starting with this final statement here. Let's let f of x equal the absolute value of x squared minus 4, and let's let that be continuous at x equals 2. So what we're going to do is take f of x, and even though this is saying f of g of x up here, I could still rewrite this f of x as a composition of functions. So in this case, I'm going to call it, separate them into g of x and h of x. So g of x I'm going to let be the inside stuff here, so that's that x squared minus 4. H of x I'm going to let it be the outside portion, which is just the absolute value of something, so in this case the absolute value of x. Therefore, f of x can be written as h of g of x, so the absolute value of the g of x function that's right here. So I want to go through a couple questions. Going back up to the very top, if g is continuous at x equals c, well, in this case, it's x equals 2. So is g of x, so I'm going right back up here to x squared minus 4, continuous at x equals 2? Well, yes, because g of x is a parabola, it's continuous everywhere. And then we could fill this in and say, well, g of 2 is going to be 2 squared minus 4, so that's going to be 0. But we also know that the left-hand limit is going to equal the right-hand limit, so the limit exists as x is approaching 2 and the 2 are equal to each other. Now, is h of x continuous at g of 2, which is 0? So if I were to substitute in a 0 here, think of the absolute value of x, that's graphed that way. So right at 0, yes, we have a point that exists. The limit at x equals, as x is approaching 0, exists. So we would say yes. Therefore, f of x, which is equal to h of g of x, is also continuous at x equals 2. So it's just a way to look at, and in a way too, we could look at domains of these as well. So we're looking at the domain of each one just to see if I asked you a question on the domain of f of x, we're looking at the continuity as well. But again, we just have to slowly, carefully go through this theorem right here. And it's not always going to be the case that we have to decompose a function as this, but it's helpful. All right, and then another theorem, this was on page 79. It's called the intermediate value theorem for continuous functions. And a lot of these theorems, after you look at it, it's kind of like one that you just know it makes sense, but they're really taking the time to make sure we understand this. So a function y equals f of x that is continuous on a closed interval from a to b takes on every value between f of a and f of b. And then this is best illustrated with a graph. So I'll talk about what's over here on the left in a moment. Go ahead, pause the video, and make a sketch of this graph. All right, so what this is saying really is if we have a value, let's say we have f of c that I'm just going to write somewhere over here and then draw over to here. So everything between f of a and f of b, I will have a value in between a and b that's going to take this on. So, and I'm not worried about anything that dips below or above. All this is saying is that if this function is continuous on a closed interval between a and b, it takes on every value between f of a and f of b. So I could have an f of c be anywhere up here, what I have highlighted in blue, and then I know I'm going to get a value of c somewhere in between the open interval between a and b. So in other words, we'll call this like y sub 0 or y naught here. In other words, if this y value is between f of a and f of b, then it's going to equal some f of c for some c in this closed interval between a and b. So for any of these y values that are here in blue, all of those are going to show up between f of a and f of b, which kind of makes sense. We see that clearly. And then that tells me if I go straight down to the x-axis, I'm going to have some value in between a and b. It's never going to fall outside, but it will take on any value between f of a and f of b, and then I will definitely have a c value that's between a and b on the x-axis. All right, so just a couple emphasis on the theorems that we've seen throughout this section. Go ahead and continue on logs day 8, and then on pages 80 and 81, do the following problems. So I will be giving a chapter 2 test sometime next week. More information will come on this. Please let me know, guys, if you have any questions.